Hello everyone, I'm Max and welcome to our third lesson, linear equations, inequalities, and absolute values. So far we have learned about expressions. They are formed in a way so everything is on one side, or in one piece. We put the equal sign, and after it we continue solving said expression. But with equations we have two sides. So on both sides of the equivalent sign, they are filled with numbers, variables, basically the terms. Basically, an equation is when you equivalate the value of two expressions, aka take two expressions that have the same result and put them on each side of the equal sign. Now, we will learn how to solve linear equations. First, we have to cover some rules. Basically, combining like terms, that stays. Next up is we simplify brackets. We also had this before, so hopefully we know how to do it. Next up is whatever you do to one side, you must do to the other. It's a very important rule because they are equations for a reason. Both sides are equal. Equations could also be explained as if we put two expressions on a graph, about which we will learn more about in like later lessons, I think in 2 or 3. Then take the other side of the equal sign, whether it's a value or an expression, graph it on the same scales, and then the intersection is the result or a value of the variable. Same goes for the inequalities, but the result will be slightly more different. We will see exactly what when we get to inequalities. So, on this example, I will show you how we do the same thing on both sides. So here we see we have two expressions, 7x plus 3, and the second one, 3x minus 4. We equalize them, whatever the word is, and we got an equation. 7x plus 3 equals 3x minus 4. Now we can figure out what x is because there is only one variable and one equation. More about this in the next lesson. But for now, this is all we need. First, we would like to move the 3x to the left. How do we do that? By subtracting it. Okay, we can subtract on the right side, and we have minus 4, but then it wouldn't be an equation if we didn't do the same thing on the left. Meaning, we take 3x on both sides, so I put subtraction on both sides, marked it orange. So we get 7x minus 3x plus 3 equals 3x minus 4. We can do this with any number. We could add 5, even though it doesn't help us in this case. But we could, as long as we do it on both sides. So now we have x and x on left and x on right. We have isolated the variables on the left side. Now we gotta get all the numbers to the right. So we will subtract 3 on both sides again, giving us this. Now we can cancel out the 3's on the left and 3x's on the right. And when we add up together everything that's left, we get 7x minus 3x is 4x, and minus 4 minus 3 is minus 7. Now, to truly get the value of x, we divide both sides with 4, which gives us minus 7/4. Next up is to remember inverse operations. So if we have plus 3, like I showed you here, plus 3 was here, how do we cancel it out? The inverse rule, or the inverse property. If we add the opposite sign of that number, so maybe that was confusing, but if we add on top of plus 3, we add a minus 3, they cancel each other out, meaning we effectively removed it from one side of the equation and moved it to the other. Same goes for multiplication and division. As we showed, when you have 4x on left and 7 on the right, you can divide by 4 on both sides, and you'll be left with x on left and 7/4 on the right. The next rule is that if the variable cancels itself out, then no number is the solution. However, it depends. We have two possibilities here. The first possibility is the variable just cancels out, and we have 2x equals to 2 times x plus 2. We solve the brackets. We have 2x equals 2x plus 4. We subtract 2x on both sides, and we get 0 equals 4. However, 0 cannot equal 4. That just doesn't make any sense, meaning that there are no solutions, because whatever you put in as x, it doesn't influence the solution of the equation of 0 equals 4. Meaning, for this equation of 2x equals 2 times x plus 2, there is no solution. However, the second possibility is when both variable and the numbers cancel themselves out, as in this example, 2x plus 4 equals 2x plus 2. If we divide both sides by 2, we get x plus 2 is x plus 2. We take away x and we take away 2. So I just combined both steps into one. And we get 0 equals 0, which is correct. Ergo, every real number is the solution. So far we're focusing on real numbers. We could also put in complex numbers. But let's stick with the real numbers for now. We haven't learned complex numbers just yet. Now let's go to the examples. First example is x minus 5 is 9. So we will remove the minus 5 on the left by adding on both sides, which gives us x minus 5 plus 5 equals 9 plus 5. We see that 5's cancel each other out. We get x is 14. There are two possible types of answers. First is x is 14, and the second one is the result is this squiggly brackets 14. We could also put x is an element of the set, which I will show you later on. But I prefer the simpler markings of x1 is 14. If we have more x's, for instance, if there were 3 x's, you could say x1 equals 14, x2 is, I don't know, 5, and x3 is minus 3. That's just an example, which I prefer, honestly, because you just have a better vision of overall the results and how many there are. But to list them in a way that's more compact, this second one is more correct. However, x is the element of the set is the most correct, but it also depends on what your teachers teach you and what they want you to know on the tests. So I'm not gonna say there's only one correct answer to everything, because usually there isn't. Except in set equations, there is just one answer, of course, as long as they're linear. I'm not gonna complicate. Basically, use whatever your teachers want you to use, but there are multiple ways to mark the result, just to have that clear. Now to get to the example number 2. Here we have x on the right side, and we have 17 equals 2x plus 1. So we don't have to move x to the left, because it doesn't matter on which side it is. It's an equation, which means that even if we change where the x is and the numbers are, it's all gonna still be the same as long as we follow the rules. But first, let's take care of separating the variables and the numbers. We will take away 1 on both sides, which gives us 17 minus 1 equals 2x plus 1 minus 1, which is 16 equals 2x. Now we divide both sides by 2, and this gives us 8 is x. Or, to order them around, x equals to 8, which is the result in this example. Now for example number 3, we have variables on both sides, along with the numbers on both sides. To solve this, we want x's on one side and numbers on the other, just like with all the previous examples. But for this, we will move 2x to the left by subtracting it on both sides, giving us 3x minus 7 equals 5. Then we will add 7 on both sides, giving us 3x equals 12. Now we can divide both sides with 3. We get x equals 4. How do we know why this is correct? How do we visualize this for those of you who prefer more hands-on approach or a visual learning style? Let's graph it. We haven't really covered graphs yet. We will in 2 or 3 lessons. But linear equations mean that they present a function or a line that's linear, a straight line. So this is a formula of one of those straight lines. In this case, the black one, and this is the red one. So 5x minus 7 is a very steep black line. And 2x plus 5 is a very, well, still very steep, but less steep than the black one. And it's red, and it's going like so. They intersect in the point 4, 13, meaning that if you insert 4 as x in both sides, the result will be 13 equals 13. But how do we know which result is the correct one? Well, since the variable is x, unless specified otherwise, it will always be x. So if we had 5a minus 7 is 2a plus 5, we would look at the x value. The y value would be more useful in functions, but we're not there yet, and really, unless the teachers specify that you should be looking at the y value, which they never will because they will never want that from you, in equations of course, you will be looking at the x value. So how do we know this is the result? Because these two lines intersect in this exact point. They cross each other. In the next examples, primarily in inequalities, and maybe even better on higher order equations, we will see that there can be more than one point where the functions or the lines cross. And in inequalities, of course, there is not just a line, but we will see in a bit what I mean by that. Next up is inequalities. The only difference, well, the biggest difference is that instead of the equal sign, they have lower or lesser than, greater than, lower or equal, greater or equal to signs. So whatever is on the left side is, in first example, lower than the right side, 20, meaning that the solution to the left side, if you put in x is 5, 2 times 5 is 10, minus 1 is 9, which is still less than 20, this means that x is definitely one of the solutions. This opens us up to more than just one answer, but we will see in a bit what I mean with that. Here we have to be careful, unlike with equations, when we are multiplying or dividing both sides by a negative number, because the inequality sign flips. And also we have to be careful, just like with equations, when the variables cancel each other out. Now, to explain more about flipping the sign, let's take minus x is less than 3 as an example. To get plus x is lesser than or greater than the number, we would want a positive x, of course, so we will move the x to the right by adding it on both sides, then subtracting 3 on both sides, which gives us minus 3 is less than x. Now, we can mirror that to write it in a more familiar way, since if a number is lower than the other number, so a is lower than b, then b is higher than a. That type of mirroring effect. So these two are completely the same. This is just better visually to get a feeling of what the value of x is. But is there one operation that we could do to get minus x into x and 3 into minus 3? Well, the answer is yes. We multiply by minus 1. And since we would get from minus x is less than 3, we would get x is less than minus 3, which doesn't make any sense, because in this example, we already confirmed with addition and subtraction. We know that 0, for instance, fits the criteria here, and we know that's correct because we got it the long way around with no mistakes, meaning that if we were to multiply just by minus 1, we would get x is lower than minus 3, 0 is not lower than minus 3, which means we have to turn the sign around. So basically this addition and subtraction is the long proof of why multiplying by a negative number turns the symbol around, which you have to be actually very careful, because there's a lot of examples where people solved it incorrectly just because they forgot this one turn. Now, for steps to solving inequalities. First of all, treat it like a regular equation. You can move around numbers, you can multiply, you can divide. You have to separate variables from numbers. You just have to be careful with negatives, especially multiplying and dividing with them. And the most important part, writing your answer or the solution as an inequality. So in this case, x will not be 3, it will be greater or equal to 3. That's why we have the appropriate signs in the inequality. We can also graph the solution on a number line or a two-dimensional graph, which is what I will do, I think, for every example from now on, to show you what the results are. There's also one more trick that I'll show you in a bit, and it's very useful and very important to know what the solution even is, because right now you may not know it, but there are a couple of complications that you're bound to run into. Let's first example, x plus 4 is less than 10. Plain and simple, we subtract 4 and we get x is less than 6. For this inequality to be correct, because there is no equal sign under it, x can be any number that is strictly lesser than 6. So 5.9 repeating works. Any number that is below 6 and isn't 6 itself works. No matter how close to 6 you get, as long as it's not exactly 6, you're fine. There is also another notation for that, which is called an interval. It's x is an element of numbers between minus infinity and 6. So if you take every number between negative infinity and 6, line them up, you would get every value between minus infinity and 6 without counting them, because minus infinity is a concept, it's not a number. I'll tell you more about that later. And 6 because it's a strict lesser than symbol, so strict has also this bracket. There's two types of brackets, again I'll explain to you in a bit, but now let's see what this entails on a graph. Here we see that unlike the lines before where we had one dot, one cross, one intersection, here we have a whole area colored with red, which with linear inequalities would be better off being presented on just a number line, like so. When you mark an interval, it's nice to thicken. Here I couldn't do it, so I just colored it with red. It's usually nice to thicken the line to make it more clear, or use brackets to know what inside the interval is. So the marking, however, is dependent on the teacher. Some only use dots and empty dots to mark the intervals, so this is an open interval. It doesn't include the specific value it's on. This is a closed interval, so if I had a square bracket around the 6, 6 would also be included. So these are all the symbols for open intervals, and these are all the symbols for closed intervals, for line, of course. On the graph, you present this with dashed line. If the interval was closed, so there was one more line here, so the 6 would also be included, you would have a full line, which again you will see in the next examples. Now, intervals. Normal brackets are open intervals, square brackets are closed intervals. Now here are a couple of examples in which I will show you when to use which brackets. So we use this sign, which means is an element of. So this entire expression would mean x is an element of an interval between -infinity and 6. An open interval of both sides, of course. Also, you don't need x is an element of, you can just write the interval. However, I prefer this symbol because it's just more neat and organized. It's not wrong, so why not use it, you know? Yeah. So for this example, x is greater than 6, we would use the open interval between 6 and +infinity. In the second example, we have x is less or equal to 6, so we have the closed interval bracket behind 6. However, we cannot use the closed interval on infinity, because infinities are not precise values. When we get to the lesson about limits and basically, yeah, when we get to the lesson about limits, etc., this is like what, 20th lesson, then you will see that infinities are not a specific value. They're an approximation of a number that is so big that it's better off reducing them to one short symbol, and so it's easier to write them down, of course. And we can't use these closed interval brackets because they stand for precise limiting or ending, which we can't because infinities are never precise. Now for the last example, -3 is lesser than or equal to x, which is lesser than 6. What the hell is this? Well, this just means that x is any number that is lesser than 6 and greater than or equal to -3, which on an interval would be presented like this. So numbers like -3, -2.5, -2, -1.9, -1, 0, 1, 2, 3, 4, 5, 5.5, 5.7, 5.99999, they're all in the interval. X can be any number out of these. Now let's see how we can use this solving inequalities. For example, number 2, we have -3x minus 6 is more than 12. We can divide the entire inequality in equation by -3. We must not forget the signs, and we get x plus 2 is less than -4. Now we can simply take 2 away on both sides, and we get x is less than -6. In an interval, this would be written like so, and on a graph, it would be presented like so. This is the two-dimensional graph where we account for the area, assuming that the y value is -infinity to +infinity. But if we just focus on the line itself, we could do the same thing. I could use the line here with the normal bracket like facing to the left, and this entire area towards -infinity would be in the interval, showing us what the result is. However, I want to use graphs more because it's a nice easing into to what we will be doing in the next lessons. Like, I think it's next 8 lessons altogether. And graphs are just better to visualize stuff. Of course, lines are easier, but we're not here for the easy. We're just here to simplify the hard and understand it. Now, example number 3. We have an inequality with variables. We have an inequality with variables on both sides. Here so, -2x minus x is less than or equal to x plus 3. Here again we have two functions, two lines, and we have to find which part of the line is lesser than or equal to the second line. So before that, we had a cross between lines, we had one point. Here we're looking for the entirety of the line that is under the other line, which I will present on a graph in a bit, and we will see what I mean exactly. So first we take x on both sides, we subtract it, and we have minus 3x minus 6 is less than or equal to 3. We add 6 on both sides. We get minus 3x is less than or equal to 9. Divide by minus 3. We get that x is greater than or equal to minus 3. And now here I have also cut the recording and added in the graph. So we see the right side of this inequality equality part is colored blue and it's going up, and the red line is going down, which is minus 2x minus 6. And now, oops, so basically this inequality slash equality states that the y value, which is the value of the result of this expression, so the elevation of this function from this line, we're comparing that y value between the two functions, or between the two lines. As in, if we take x is minus 4, we see that red line has a positive elevation and blue has negative elevation. However, this inequality wants to know where the elevation of the red line is lesser than or equal to the elevation of the blue line, which we see right here. This is where the elevations switch. So from this point onward to the right, this is when, as we see here, all the x's are included into the interval. So we compare the y's to see when they satisfy the condition of this, and at that y value, so the up-down elevation or up-down value of the graph, from that point on, when that inequality stays, we take the axis from that point on. Hopefully that makes sense. If not, it's not as important here. You just need to do the math part. For graphing, we will do more in the next lesson and the lesson after that and the lessons after that. And we will see exactly what this means. This will be nothing. This entire thing will be simple, logical. You could do it at 3 a.m. if I woke you up. That's simple. I promise you that. Next up, we have absolute values. You may be wondering why I involved them here. Well, they also have to work with intervals and complex stuff. So in equations, we got lines on a graph or points on a number line. And when we worked with inequalities, we got areas, intervals that would be above, under, left, right of the line that we could get if we change the inequality itself into the equation. Since they both have the same form, you just state in the inequality if the area you want to focus on is above or under or greater than or lower than the equation or the expression we have given. But now absolute values add some extra complications to this, and you will usually see them in these examples as well. And in functions, they do serve quite a big of a purpose, actually. So why not learn what they are now? And of course, when we get to complex numbers, which is a whole separate deal. Anyway, first let's see the properties. By definition, absolute value of a equals to a if a is greater than or equal to 0. An inequality, now we know what this means. And an absolute value of a is equal to minus a if a is lesser than the 0. Now, next property is addition and subtraction. We know that if we have a bracket a plus b, that equals to a plus b outside of it. However, with absolute values, it's not exactly the same, as the absolute value of the sum of a plus b is not always equal to the absolute value of a plus absolute value of b. This is called the triangle inequality. How so? Well, I drew that. Let's assume that we have a triangle with 3 sides. The basic rule for triangles is that the sum of 2 sides must be greater than the third one. So you can't have a triangle if 2 sides add up to the exact same distance as the third one. So, in this first case, the value, since we know absolute values represent a distance, so it would be the same as flattening them out, like making a curve like so. This would be the length of b. If we combine the sum of lengths, a plus b would be greater than c. Hopefully we all see this. In the second example, it's still a triangle. Approximation could be made that the sum of a and b could be c. However, technically it's still greater than c. Now, if we made a plus b equal to c, it's no longer a triangle because these 2 points would have to have a 0-degree angle, which means a plus b is quite literally the line c. Hopefully this shows you that the triangle inequality states that the absolute value of the sum is not always equal, but is lesser than or equal to the sum of absolute values. But what about subtraction? If b would be greater than a, the negative sign would make it negative. since there's no absolute value over everything. However, here it is. So if we had 5 minus 10, the left side would be minus 5 in absolute value, which is 5, which should be greater than or equal to, we would have 5 minus 10, it's minus 5, which means that minus 5 is less than 5. Okay, so it's the exact opposite. As for proof, the long way proof, I will link the video, which is a very nice short video. I think it's like 5 to 7, maybe 8 minutes long, and very orderly, very clear and easy to understand. That video will be linked in my description and the comments, so make sure to check it out if you want to know. And yeah, I won't bother you, I already stole too much time from you in this video, so let's just keep going. We still have a lot to work through. Next properties are multiplication and division. As with normal brackets, if we multiply absolute values, it's the same as the absolute value of the product. Same for division. If we divide two absolute values, we get the absolute value of the fraction. However, this again only makes sense if the b is not equal to 0, as otherwise you could not divide. Now for first example, we have absolute value of x minus 2, that equals to 5. Now how the hell would we even solve this? You may be wondering. Well, two processes. First, we need to assume the value of the expression, because we can't just plug the numbers in and trial and error it, so we need to know when the absolute value changes and when we can remove it. So if you remember the rules, if the result inside is less than 0, we put... It's basically the same as multiplying the entire thing with minus 1 to get a positive number. There's also another rule, but I will show you that in a second, and it's also mentioned in the video that I recommended, but I won't go into it, because it's essentially the same thing, just multiplying with -1 on both sides. Anyway, first solving process, let's try assuming that x minus 2 is greater than or equal to 0. So we can just copy the exact equation as was above and removing the absolute value to solve it. So if we move minus 2 to the right, it's basically the same as adding 2 to both sides, which gives us x is 7. Here we would usually check if x follows both conditions, so we would replace the x in the original equation and the condition. So the original equation is this and the condition is this. So put 7 in the first one, so 7 minus 2 is 5. Apply absolute value, stays 5, 5 is 5, lovely. And since 7 minus 2 is greater than or equal to 0, 5 is more than 0, we know that this is one of the answers, so we write x1 is 7. However, this is not the end. There's still one more process to check for, and that is what if x minus 2 is less than 0. Here we must assume that if it is, we multiply the expression inside the absolute value with -1, so we get minus x plus 2 is 5. Now we move 2 to the right, by subtracting 2 from the entire equation, we get minus x is 3. Turn them around, we get x is minus 3. Now we plug that back in, minus 3 minus 2 is minus 5. Absolute value of that is 5. Minus 3 minus 2 is minus 5, which is less than 0. Boom, take 1, take 2. Correct. Now, let's see if we solve this correctly by graphing it out. I do recommend Desmos, if I haven't said it before. It's a wonderful graphing tool. I use it for almost everything that involves graphing. But here we have a graphical representation, which would be better off on the line again, but again, I'm slowly accustoming you to graphs, since they are more and more common and useful in life. Here we see we get 2 points, minus 3 and 7. Only these two, either of them, are the solutions. And of course, we will be looking at the x value, not the y value. So if we look at the x value on this line, we see that 7 and minus 3 are both marked by this equation. This means that these two are the only results. Next up is absolute value of the sum of 2x and 3, which has to be equal to 1. Again, we will make the same assumption that the absolute value, what is inside it, is greater than or equal to 0. We copy the equation without the absolute value, take 3 to the right by subtracting 3 on both sides. We get 2x equals minus 2. We divide by 2 and we get x is minus 1. Second condition, if the expression in the absolute value is negative, we multiply it by minus 1, we get minus 2x minus 3 is 1. We add 3 on both sides, we get minus 2x equals 4. Divide by minus 2, we get minus 2. Now to graph it on the line, we get minus 2 and minus 1 as the results, which proves that we solved it correctly. But we can also check that by putting the x value in its own condition and the original equation, and that way we get the answer. Now again, we have the variables on both sides and an absolute value on 1. So in this case, we have to solve two equations, kind of. So these are the two equations that we have to solve. As I mentioned before, there's another method of applying absolute values. So if this part inside is greater than or equal to 0, you copy it as it is. If it's lower than 0, then you get this, because people usually multiply the other side with -1, because it's easier. However, I find it easier to just multiply the absolute value. It does depend on the example though, so do whatever you think is easier. I do think the absolute value multiplication by -1 is much easier, because sometimes you have more than one term on the same side, and it gets a bit more complex, and more than one absolute value, of course, and it just becomes a mess. So basically, these are the two inequalities we have to solve. You can see that if I multiply this bottom one with -1, we get the top one. But let's just go the long way, step by step, as we did it before, and see why this is the way it is, and what the results are. So, if 2x minus 5 is greater than or equal to 0, we would get 2x minus 5 is lower than or equal to x plus 1. We move x to the left by subtracting on both sides, and we add 5 on both sides. To get this, we solve on both sides the common terms. We get x is lower than or equal to 6. An interval. Now for the second condition, if 2x minus 5 is lower than 0, well, then we just multiply the absolute value part with -1 and remove it. We get minus 2x plus 5 is lower than or equal to x plus 1. We move x's to the left, subtract x on both sides. We subtract 5 on both sides. We get minus 3x is less than or equal to -4. Divide by -3. Of course, we have to remember to change the directions. And we get that x is greater than or equal to 4/3. Now we have an interval where one x is greater than and the other one is lower than a certain number. Well, sorry, greater than or equal and lower than or equal. In this case, we will take the intersection of both of those intervals. I will explain why in a second, but let's write this down as the interval itself. So x is between these two values. We write out the equation, and if we looked at the graph, the absolute value would come from above, intersect with the sum line on the value of 4/3, go under it, bounce back up at some other point and go up, and cross the straight line we imagined at around 6. But why is it exactly this interval? Because technically all numbers are accounted for. This fits this condition and this equation, and this fits this equation and this condition and this equation. So why aren't all numbers fitting this? Well, how to know exactly when to combine intervals and when to find the intersection? Well, there are a couple of methods. First is we combine the intervals when we say or, and then we take the intersection when we say and, because intersection is what the set 1 and the set 2 have, and combination is what the set 1 or the set 2 has. These are logical gates you might have learned already. I have found something simpler. Less than is an intersection because less than individual intervals. So you have two intervals from 5 to infinity and from -infinity to 10. Since it's less than, like x is less than some value, we can take the smaller part of the intervals, since between 5 and 10 is much smaller than between -infinity and infinity, you know, that type of stuff. So less than, so a variable less than a number means that the intersection is gonna be the lesser of the two. So the intersection, so whatever they have in common. If the variable is greater than some number part, then it's the combination of intervals, since the combination is greater than individual intervals. I really hope that this does make sense. So greater than the combination of intervals, so add them together into one interval or two separated by a space of nothing, and less than is intersection, so only what they share in common. But yes, I will solve one more example in a bit where I'll show you how exactly this works. Now we have to remember the common mistakes people make, and the most common one is obviously forgetting to flip the signs. For instance, minus 2x minus 5 is less than 1. We add 5 on both sides, we get minus 2x is less than 6, we multiply by -1, we don't get x is less than -3, we get x is greater than -3. Why? Just because of that proof we did several slides ago. Second mistake is wrong interval from absolute values or inequalities. So this is the example I said I'm gonna solve in a bit. I'm solving it now. The absolute value of the difference between x and 3, so x minus 3 under absolute value, is lesser than minus 2x plus 3. we have the symbol less than, which is an intersection. However, we will see exactly why this is less than. So, first assumption for the absolute value, x minus 3 is less than 0. Minus x plus 3 is less than 2x plus 3. Minus x plus 2x is less than 0, so x is less than 0. Now for the second interval, we have to assume that x minus 3 is more than or equal to 0. So we just copied the equation, or sorry, the inequality as it was, removing the absolute values. We get x minus 3 is less than minus 2x plus 3. We moved all x's to one side, we moved all numbers to the right side, we add them together, we get 3x minus 6, which again, we have less than a symbol, which means that we take the intersection. And what the intersection is, we gotta remember, what do they both have in common? If we graph out a line where every number between minus infinity and 0 are colored up, and another line which has the other color from minus infinity to 2, we would see that the first interval, the minus infinity to 0, is what they have in common, which is the intersection. So having that graph looks like something like this. Not including 0, but every other number from minus infinity to it. Time for the mini test. It's here on the screen. I wish you best of luck solving it. If you want the results, they are up in the top right corner above my name. And yes, thank you so much for tuning in today. Have a great rest of the weekend and see you on our next quest. Bye!